Would you look at that, this child has learned to walk. As you can see, we now have the sprite animations working, and I really want to talk about how it works. But first, there is a problem of serialization. As I was coding the animation system, I quickly realized that every animation entry takes a good amount of lines. Obviously, hardcoding them is not an option. And the further we'll go, the worse it will get, as we will have other kinds of data to worry about. So it's clear that we need to store them in a file and then later load them at runtime. Godot already provides a way to do this with the help of resources. And here's how you do this. First you have to extend from a resource. Then you need to name this class, because if you don't, deserialization will not be possible. And then every field that you want to export, you have to annotate with the export annotation. And because of this annotation, you also have to use static typing. So, 4 steps to make one resource. And also, it will not work with the subclasses, the ones you create with the class keyword. Any alternative, like creating a custom class with the file access or using JSON, will not work, as we'll have to interact with the PCK file that can also be embedded into the main executable. So we need to find another solution. Let's understand resources better. Aside from objects and primitives, we can also store some complex built-ins like arrays and also dictionaries. So this one is valid. And as we've established in the previous episode, dictionaries are pretty similar to objects, and in fact one can be created from the other. So our new workflow would be creating a dictionary from an object and then storing them to a resource. I've created this class called serializer, and the only field it has is the data in the form of a type dictionary. The first set of functions is the serialization. The public API will just serialize and save to a file. The whole meat is here in this underscore prefixed. It recursively goes over every property of an object and turns it into a dictionary. And if it's an object that is, built in, it just stores it as is. The next set of functions is the deserialization, and this one does it in reverse. Interestingly, we have to pass the object type, so we have to know what kind of object we are deserializing. Usually Godot would infer this from a class name, but since we don't have any, we have to do this. And okay, this all seems complete, but there's also one feature of the resource floater, which is, let me show you. It's the threaded, yes, load threaded. So it would use multiple threads to load a resource. Basically, with this function, we would not get stuttering when loading resources, which may be helpful when we load levels and stuff. Because of this, I created a function that uses the async feature of Godot. And here we need to pass the await event. Usually it's just the update frame. So it means that in the current frame it would not load a resource, but rather in a separate frame. And also this is not to be used in the same callback that called the signal. So this whole thing is complete, and let's test it. I am once again in the main process, and let's have something. Where do I begin? I think I first need to create a subclass called store. And it would have some fields, let's say var foo, that would be an int, and var bar, that is a float. Let me use the serializer, serialize to a path, which is res, this, and I call it store res. The resource would be a store new. Oh, let's give it new values. So let's test. And it should be here. All right, we can see this because it's a res, which is a binary file. I want a trace. And here we go, it's serialized, but will it deserialize? That's the question. Now that we have it serialized, let's deserialize it. And here we'll make it like this. Var store, and I'll print. And yeah, it works. But I also want to know, will it work if we do the async version? Basically, here we'll do await. Yes, it worked. When I was testing this, it just didn't work. It either broke or something, but here it works. So now we have this serializer that we'll be using for our many resources. Here's an interesting thing. Because we can store anything, a primitive, a built-in, we can also store the dictionaries, which are the entities that we've defined in the previous episode. Let's go back to this sprite component, because we're going to add animations. Generally, the way we would do this in a regular framework, we would use something like time, in this case time get ticks, msec or usec for nanoseconds. We would get the remainder, or wait, we would get the division to obtain the index. But the rendering server actually has a function to aid this keyframe animation, which is the primary method of animation in a pixel art game. It's called let me find it, canvas item, add animation slice. This function is magical. We define a slice here with its duration. The slice begin and slice end will indicate at what point these commands are valid, so it will show them appropriately. Because of this, I want to get rid of this srcrect and destdirect, because we will do it differently. I'll create a subclass called animation descriptor, and it will hold two variables. One is a sprite sheet of the entire animation, and another is an array of animations, which will be an array of dictionaries. Basically, it will hold information about specific animations. And I also need to add this. This will create the dictionary for the animation. And we're done here. Now that we have it created, we need to add it to the main component. One is a sprite, which is the animation descriptor. And another is the current animation index, which is an integer. And finally, we need to add a function to play the animation. It will accept the state since the animations are an array, so it will accept an index of an animation. And here's how the function looks like. The interesting part is here. Instead of running this constantly, we just run it once, and every animation, every drawing command is passed to the rendering server just like a shotgun. And this function just resets the animation slices to the previous state. This is how it's written in the source code. I'm not sure why, but it works. And that's it. That's the entire thing. Now this is complete. Because the logic is now handled by the controller, basically instead of the input components, we will have full-blown controllers. The first one being the player controller. I have completely rewritten the entire input system. Now it will manage both the movement and the sprite component in the sprite animations through these two subclasses. One will just do the physics, for now it's just nothing, and another one is, well, handles some complex state. This one is just for debugging, don't mind it, but everything else is handled by this controller. And I'll add more because obviously this is just for movement, but there are also other states like interacting with an NPC and entering the dialogue state, or even just going to the inventory. As you can see, I added the animations, and now I'm serializing them to this Frisk test. Obviously, that's not how we're going to be creating animations. I'll probably add editors in the future once we figure out the UI and stuff. But for now, this is how we do this. Yeah, looks ridiculous. Okay, so it's saved, and let me go back to the assets. So here's the trace, and as you can see, it's all stored in here. Now, this one does not matter anymore. I can just comment it out. And now I need to add the entity. Entity equals, I already destroyed it, but doesn't matter. Entity manager, let's create the entity. Now, since the controller depends on the sprite to be initialized, we have to create the controller afterwards. So the first one is the sprite component. And we need to load the descriptor. Now I'm going to show you the serializer in action. Let's deserialize async, and we'll just use the res assets, frisk test trace. Oh, and we need the object type, which is the start component, animation script, that's right. And here the input. Wait, no, the player controller, which will have the speed. I think it's like this. And let's see it in action. I think it should work. Okay, so here you go. Here it says a bunch of stuff, but that's just for logging, because I had to figure out how this whole thing works. But yeah, this is the animation we have. This is how we do the camera, but for now it's just, simple attachment to the center. And yeah, now we follow the player. What now? Well, basically this frame-based animation is complete. However, I want to mention something. It does have this weird flickering or something where if you spam press the button, it just behaves weird, because as I can see, the rendering server somehow aligns the frames to some internal timeline, and that's why it looks so weird. Instead of the animation beginning when we press, it just begins from the moment that it left off. So you can see this halting problem in action, but overall it looks okay. I'm pretty sure the same kind of principle we will apply to the tile maps, and we're getting closer to creating the test scenes. But that's it for now. Hope you learned something new, and have a good day.